Wanted to find out, is Lightning McQueen really the fastest car in the world? And what we did was we borrowed some toys from my 3-year-old son. We ended up borrowing Lightning, Raoul, and Shu. And we sent him down a little track where we had marked off certain distances. We timed it using a slow motion camera app, pulled out the times, corrected for it, and figured out instantaneous velocities and accelerations. In other words, we did that, and then we decided what it's going to be. So, a simple way to figure out velocity is it's just simply the change in position over the change in time at those positions. You get a unit, that's the distance of something, distance per time. The next step is acceleration, which we'll come back to later. How do you relate the two? Acceleration is simply the change in velocity per the change in time, or whatever the distance is over seconds or time squared. And that's basically how calculus was invented. So this is looking at the velocity, simple position, time once everything was corrected out, and we have our 3 cars. And what we see here is the white Shu Todoroki is the fastest car. Lightning McQueen, through going sideways, backwards, and everywhere else, ended up being the slowest. Then if we look at, and this is just, we did this at 3 different heights. This is just the tallest height. It pretty much looks the same no matter what height you look at. This is the acceleration profiles for the same 3 cars at the same 3 heights. You sort of see similar, something really weird going on at the first. But in this case you see the velocity on the y-axis and you still see time. This is sort of a comparison of just one car from the highest position. You see the velocity, this pretty linear, but the acceleration sort of goes up at a faster rate, goes even faster, then makes an even more huge jump as we get to the bottom of our little ramp. As I said, we did this at different elevations. So again, we just took one car, compared the 3 heights. You'd see something similar for all 3, whatever the pathway that they've made. These are sort of the accelerations. Again, same car, 3 different heights. You do see a trend that the highest is always the greatest, whether it's velocity or acceleration. Lowest is always the slowest. And now it's time for our thoughts.
All right. Our thoughts on this experiment. First, what we expected before we even started. Let's kick off.
I was sort of expecting something similar to what we had as far as because it was a plane, so something's fairly straight for its velocity. And yeah, I was expecting something a little bit different from acceleration. I think I possibly overplanned a little bit and wanted all this sort of data, and ended up just simplifying it down to, let's just see how the time difference between the 2 points.
Mm-hmm. Yeah, it was a lot of...
ended up being much simpler
Yeah.
than what I was thinking it out to be. And the only way, and then that's sort of what we're struggling with, is how to sort of separate the 2 concepts, acceleration and velocity. And we're always talking about how, let's look at the units. Mm-hmm. And if we figure out the units of the 2, you see that velocity is a rate, and acceleration is the rate of the rate.
Mm-hmm. Yeah.
And you can't necessarily pull them completely apart because the one comes from the other.
Yeah, I feel like
that's an easy way to interpret, the similarities or difference between acceleration and velocity. But sometimes, like in, certain physics exams, you can kind of get into the whole plug and chug thing just to get the unit you want, and maybe you're not even thinking about the difference between the two. But I think the point of this, like what we did, seeing the different points along that ramp and the velocity and acceleration for each kind of drives, home the point that they are different. So just doing it, I think, is a good way to separate the two.
Mm-hmm. And I thought, like the visual, I'm a very visual learner. I thought seeing this in action, the ramp, with the cars, would paint a better picture for me for acceleration and velocity.
Yeah.
One thing I think would be better is if we had a longer track.
Yeah.
Ours was pretty short, and the camera did help to kind of break that up, but it would have been better if we could find, I guess, the resources to make a nice long track, so then we can really break it up and really see the change in speed for each car.
And what's change in speed?
Change in speed is acceleration.
Yay!
I'm learning. We're learning.
See, we have to be careful with our words.
Exactly.
Because one way we started thinking about presenting this maybe to students is, because it goes back to the whole I hate math lecture that Matt gave, was instead of making it an I hate math lecture, let's make it a I hate vocabulary word. Mm-hmm. And if you can pull out the unit of whatever term you want, whether it's Newton, acceleration, joule, you can then go set up a problem with a whole bunch of givens, and if they can piece together, okay, I need this one, these three things to make this unit. Mm-hmm. And then you can basically say, okay, now do you have to multiply, divide them together, and simplify a lot of the math anxiety, I would say.
I think that's one of the biggest problems, too. So what happened, that we kind of showed with our graphs, what happened with our experiment here. So, let's see, I have to look at the graphs. How would you interpret them?
I'd say we had like a linear motion as things pulled down. They were accelerated, basically started from rest, and they accelerated basically. This is where I got obsessive about the triangles that we didn't use, but due to gravity, because we measured it in a linear fashion, we could figure out the acceleration just by measuring the distance, the points, and the slow motion, and how much time it took to get between each point.
Right.
Let's see. What's the
any difficulties that we had?
I guess maybe like the release time, all the calculations, because we had a lot of points.
It actually, and I can speak to that because I did it in the slow motion. Yeah. Once the slow motion, it didn't take that much, and you sort of, by the second one, I was getting on a cue, and there's a joke in the email when I was talking about this. You don't give Natalie a gun. Her index finger is really twitchy in slow motion. And I don't think she knows it.
It is hard for me to sit still, so maybe that's, I don't know.
So I had a really good cue, and her index finger started to twitch. It's like, oh, release time's coming.
Yeah, and like I mentioned before, the track size. Like, so if we had the longer track, we could get a better idea. And what relationships we saw. So this might boil down to our relationship with velocity and acceleration.
Yeah. I think the biggest thing that it always surprised me is that you can have this like at the end, we can have this all our points basically set at the very last, from our last little designated arbitrary line to our finish line. There is a huge change in acceleration, but not that great a change in the velocity. And that's sort of an underlying thing, is that you have these great, huge changes in velocity. These very slow changes in subtle changes in velocity, but they can be a result of very dramatic acceleration, like order of magnitude differences.
Yeah.
how this helps students separate velocity and acceleration, kind of with help from our graphs. That's the million-dollar question. How can we make this make sense to students? Without being too dull, I guess, and too mathy. That's the hardest part.
I think, because creating them is basically, the historical thing is I sort of did what Newton did. It's literally, I looked at, here's point 1, here's point 2, subtract them. So here's the time at point 2, time 2, and subtracted them. And without, somehow getting them to figure out that, which was 1650s science. And that's basically how it worked, and you can come up with the answer eventually.
Yeah, I mean, I think it's just much more useful doing it like this. Like you said, you're a visual learner, but sometimes for some teachers that means drawing a diagram. And that doesn't necessarily help because you can't really picture it like you could once you're doing it in 3D model.
And I think somewhat the ability to actually see it in slow motion, so you can have, something we couldn't quite, we could have done in the last experiment, but because we couldn't mark the heights. Here, because we arbitrarily marked the heights, we could obviously say, here it is, once we zero out the times, here's time point 1, time point 2, and that corresponds to distance 1, distance 2. It's an added benefit that, say, like I said, we're doing 1650s. They didn't have this ability in 1650. We have it.
I don't know, my last little bit, and I hope it makes sense. How I make sense of this in my head when I separate the two, velocity and acceleration. So you have a car, it's accelerating, it's going faster and faster. And then let's say it levels out at 60 miles an hour. Doesn't go faster, doesn't go slower. Has an acceleration of 0. But it still has a velocity because that's the measure of speed at one instance. So while your acceleration is 0, you could still have velocity. How else can I break this down?
I like the example because it's, you press the pedal in the car,
Goes.
and you hold it at a certain point. You stop pressing it, you sort of release the pressure, and it holds.
Yeah, I think it just comes down to using, like, real world, like football. I remember we talked about football in my physics class to learn about it. Pushing a pedal in a car. I think to just help students visualize it better, or separate the two.
Stop this one. Just a couple of little miscellaneous endnotes. Some of the slow motion clips are available on YouTube. I didn't feel like paying to put the app to download the data. And according to the Cars 2 guide, because it's popular in my house, the car that came out the fastest in our study was the fastest. Lightning McQueen, as you'll see, sort of went sidetrack. And the actual car that was second fastest in ours is actually the slowest. And you sort of see in our graph the large acceleration values can result in small changes in velocity.